already had the floor at the opening ceremony, and he's a Nobel Prize winner. So as a future economist, as people who learn some economics, probably you've not only heard his name, but also are aware of his achievements in our science. But still, for the protocol, this is Professor Eric Maskин from Harvard, a Nobel Prize winner in economics. Please.
Good afternoon, everyone. It's a pleasure to be here with you in St. Petersburg today. And I thought I would take this opportunity to tell you a little about the subject that I've spent a lot of my career working on, and that's mechanism design. Perhaps many of you don't know what mechanism design is. That's perfectly fine, because what I'm going to try to do is to tell you enough about it today so that by the end of the lecture, you will not only know what mechanism design is, but you will have some explicit examples in mind in which mechanism design plays an important role. I'll start by trying to give a short definition of mechanism design, but if you're like me, definitions don't really provide very much information. They tend to be too general and too abstract. Instead, what I'll do is spend most of my time on a few concrete examples, and I think the examples will illustrate best what mechanism design is all about. But let me make an attempt at a definition. And what should I point this at to make it work? There we go. So the theory of mechanism design is what I would call the engineering part of economics. Usually what economists do, what I would say 90% of economics is about, is looking at existing economic institutions, trying to understand those institutions, trying to explain or predict the outcomes that those institutions generate. This is what's called the positive or predictive part of economics, and it's very important, and as I said, it's maybe 90% of what economists spend their time doing. But I'm actually interested in the remaining 10%. In the remaining 10%, in mechanism design, we actually reverse the direction. That is, we start with the outcomes. We start by trying to specify the outcomes that we would like to achieve. Those are our goals. And then we work backwards to ask, could we design, create institutions, mechanisms that would achieve those goals? And if the answer is yes, what form would those institutions take? And this is what is called the normative or prescriptive part of economics. It's not as popular as the positive part, but it's the part of economics that I happen to like the best, and I hope I can persuade some of you that it's worth studying. Okay, so that's a very general definition, and maybe it doesn't tell you very much. So let me go immediately to a little example. Let's imagine that you have a cake. You're a parent, a mother, or a father. You have a cake that you want to divide between two children. And we'll call the children Alice and Bob. And your goal is to divide the cake so that each child thinks that his or her piece is at least as big as the other kids. That means that Bob should think that he's got at least half the cake, and Alice should think that she's got at least half the cake. And we'll say that if you achieve this goal, then you have attained a fair division. So your goal is to attain a fair division. Now, how do you do this? Well, if you know that the children see the cake the same way that you do, then there's a simple solution. You can just take a knife and cut the cake exactly in half, exactly from your point of view, and then give each kid one of the pieces. And because we're assuming that the children see the cake the same way that you see the cake, this will solve the problem. The problem in reality, however, is that children almost never see the cake the same way you do. You might think that you've divided it equally, but Bob may well think that Alice's piece is bigger. So here's the mechanism design problem. You want to achieve a fair division, but you don't actually have enough information to do this on your own. You don't know how the children see the cake. That means that you don't actually know what a fair division is. And the mechanism design question is, despite this lack of information, is there a mechanism that you could carry out that would result in a fair division, even though you don't know what a fair division is? Well, it turns out that this problem is actually very old. It goes back literally thousands of years. If you know the Old Testament of the Judeo-Christian Bible, you may recognize this cake division problem as being the same as a problem that Lot and Abraham had. Lot and Abraham were two men who wanted to divide some grazing lands in a fair way between them. And just as the Old Testament states the problem, it also gives the answer. And as you will see, the answer is extremely simple, but it's also extremely clever. And that is the hallmark of mechanism design. In general, the answers tend to be really quite simple, so simple that after you see them, you say to yourself, well, I should have thought of that myself. But although they are simple, they tend to be really quite ingenious. And that's one attractive feature of the field, the ingenuity that is involved in finding these mechanisms. Well, in the case of dividing cake, here is the solution. What you can do is to give the knife to one of the kids. You can give the knife, say, to Bob, and Bob will cut the cake. And then after he cuts the cake, the other child, Alice, gets to choose which piece she takes for herself. And then Bob gets the other one. So this, you may have actually seen this mechanism used. It's called the divide and choose mechanism, and it's used a lot in practice. And I claim that this solves the problem. And here's why. When Bob is cutting the cake, he has a strong incentive to cut it in such a way that the two pieces are exactly equal from his point of view. Why? Because if one of the pieces is bigger, he knows Alice is going to take that one, and he'll be left with the smaller piece. So Bob will try to cut the cake so that whichever piece Alice takes, he's happy with the other one. So Bob will think that he's got at least half the cake, and Alice will think that she has at least half the cake because she gets to choose her favorite piece. And so we've solved the problem. The divide and choose mechanism solves the problem. Now, you may say that this is a very, very simple problem, and yes, it is, but nevertheless, it's already complicated enough to illustrate some of the main features of mechanism design. First of all, and this is important, the mechanism designer doesn't know in advance what the optimal outcomes are. Before the cake is cut, you don't know what a fair outcome is. You don't have enough information to do that. And that means that you can't just cut the cake yourself. You have to proceed indirectly through a mechanism. In the case of the cake example, the mechanism was the divide and choose procedure. But there's an additional complication, which is that your goal may be to achieve a fair division, but that may not be the goal of the participants in the mechanism. Bob and Alice don't care about a fair division. They just want as much cake as they can possibly get. So when you design a mechanism, you have to take into account that your goals may not be the same goals as the participants. The participants have their own objectives, and so the mechanism has to be compatible with those objectives. In the language of mechanism design, we say that the mechanism has to be incentive compatible. Okay, so that's our first example. Let's go on to something a little bit more complicated and also more important. And this second problem is going to be a telecommunications example. About 25 years ago, many countries around the world realized that it no longer made sense for the governments to completely control the radio spectrum. The radio spectrum is the spectrum of radio frequencies on which broadcasting is possible. And up to the mid-1990s or so, most of these radio frequencies were controlled by the government in most countries in the world. But this was at a time when telecom companies realized that they could use these frequencies for mobile telephones, for satellite television, for all of the many modern technological miracles that we now take for granted. These didn't exist 25 years ago, but there were telecom companies that wanted to make them exist. And so what governments did was to transfer the use of these radio frequencies from the public sector, from the government sector, to the private sector. So let's look at an example of this. Let's imagine that there's a particular band of radio frequencies that the government wants to transfer to one of several telecom companies who are interested in these frequencies. We'll say that the right to use these frequencies for broadcasting is a license. And let's imagine that the goal of the government is to put the license into the hands of the telecom company that values it the most. The reason why the government might have this goal is that the company that values it the most is likely to use that license to create the most value for society. This is what economists would call the efficient outcome. When you're allocating a resource to one of several companies that are interested in this resource, if it goes to the one who values it the most, we say that's the efficient outcome. So the goal of the government is efficiency. But let's suppose that it doesn't know which company values it the most. What could it do? Well, the simplest mechanism would be for the government to ask each company, how much do you value the license? And then to give the license to the company that quotes the highest figure. But you can see that this mechanism is not likely to work very well, because if companies understand that their chance of getting the license is bigger if they quote a bigger number, well, then they're going to exaggerate their values. And if all of the companies are exaggerating their values, there's no guarantee that the company that really does value it the most will get it. So this mechanism, although simple, is not going to work. Well, the government could use a somewhat more sophisticated mechanism. It could have each company make a bid for the license. A bid is a statement of how much the company is willing to pay for the license. And the government could award the license to the high bidder, the company making the highest bid, and it could actually have that company pay its bid. Well, this mechanism is going to work better than the first, because now companies are not going to exaggerate. If I'm a company and the license is worth $10 million to me, I'm not going to bid $12 million, because if I did bid $12 million and I won, I'd have to pay $12 million, and that's too much. It's only worth $10 million to me. So companies won't exaggerate anymore. But unfortunately, this mechanism also fails, because now companies have an incentive to underbid. Let's see why that is. If the license is worth $10 million to me, and I actually bid $10 million, and I win, well, I'll be getting something worth $10 million. The asset is worth $10 million to me, but I'm paying $10 million. My net profit is zero. I might as well have not bothered participating in the first place, because I get nothing out of participating. So I'm not going to bid $10 million. I'll bid something less. Maybe I'll bid $8 million. If I bid $8 million, that reduces my chance of winning, but at least if I do win, I'll have a nice $2 million profit, 10 million minus 8 million. So that means that all of the companies are going to be underbidding, understating. But if they're all understating, then once again, there's no guarantee that the company that values it the most will get it. Well, at this point, you may be asking yourself, is there some mechanism that gets things right? In the first mechanism, companies overbid. In the second mechanism, companies underbid. Does there exist a mechanism where companies bid exactly what the license is worth to them? Well, it turns out that the answer to that question is yes, there is a mechanism. It's not thousands of years old. In fact, it was discovered only about 50 years ago by the American economist William Vickrey. And this Vickrey mechanism, like I was saying before, shares the quality that it's very simple and also very clever. And here's the solution. What the government should do is to have each company make a bid, and the government should award the license to the high bidder, but instead of having the high bidder pay its own bid, it should pay the second highest bid. So for example, if there are 3 bidders and one bids 10 million, one bids 8 million, and one bids 5 million, the company that bids 10 million should win because that's the high bid, but it should pay only 8 million because that's the second highest bid. Now I claim that this mechanism, which is called the Vickrey mechanism or the seconds bid mechanism, solves the problem. Because now companies will bid exactly what the license is worth to them, not too much, not too little. Let's see why this is so. First, notice that a company no longer has any incentive to underbid because it doesn't pay its bid anyway. Underbidding is not going to reduce the amount that it pays. If the license is worth $10 million to me and I reduce my bid to $9 million, if the second highest bid is $8 million, I pay $8 million either way, whether I bid $9 million or $10 million. I don't improve my payments by underbidding. And furthermore, if I underbid, I run the risk of losing the license altogether. Suppose that it's worth 10 million to me and I underbid and I bid 7 million. Well, if some other company bids 8 million, now I will lose. If I had bid what it was really worth to me, 10 million, I would have won and I would have had a $2 million profit, 10 million minus 8 million. So underbidding not only fails to reduce my payments, but it also runs the risk of my losing the license altogether. So I certainly do not want to underbid. But I also don't want to overbid. If the license is worth 10 million to me and I bid 12 million, and some other company bids 11 million, well, yes, I will win by having overbid by bidding 12 million, but I'll have to pay 11 million, and that's too much. The license is only worth 10 million to me. So I don't want to overbid because that puts me in danger of overpaying. And that means the only thing left for me to do is to bid exactly what the license is worth to me. But if all companies are bidding exactly what the license is worth to them, then the winner must be the company that really does have the highest value. And so once again, the problem is solved. So I've shown you 2 examples. Let me show you one more example. And you will notice that the second example was a little bit more complicated than the first. Well, the third example is going to be a little bit more complicated than the second, but not too much more complicated. So for this third example, let's look at a society which is interested in choosing an energy source. To keep matters simple, we'll suppose that this is a very small society. It just has 2 people. if you studied some economics, you know that economists love to have examples where there are very small numbers of people. It's not because we believe that society is really that small, but it's just easier to do the example with two people. So in our case, we'll call the two people Alice and Bob. You've heard those names before. So Alice and Bob are our two people, and they're consumers of energy. And there's also an energy authority whose job it is to choose the energy source for Alice and Bob. And let's imagine that there are 4 possibilities. There's natural gas, there's oil, there's nuclear power, and there's coal. And I realize that this is not the most ecologically sensitive choice of energy sources, but remember, it's just an example. So the authority has to choose one of these sources, and it wants to choose the source which Alice and Bob like the best. But the authority doesn't know what Alice and Bob like. Let's imagine that there are 2 possibilities for what Alice and Bob like. We'll call them 2 states of the world. In one state, Alice and Bob care mostly about current consumption. They don't put too much weight on the future. And in the other states, they care mostly about future consumption, not so much about current consumption. Now, Alice cares mostly about convenience, so how easy the energy source is to use. So that means that in state 1, she likes gas the most because that's the easiest to use, and she puts nuclear power down at the bottom because nuclear power is quite cumbersome to use. If you had a nuclear-powered car, for example, that would be quite complicated. But that's only in state 1, where she's focused on current consumption. If she were in state 2, where she cared mostly about consumption in the future, now she would like nuclear power the most because she believes that there are going to be improvements to technology which will make nuclear power much easier to use in the future. And now oil comes down to the bottom. Let's suppose that Bob cares mostly about safety. So in state 1, if he's concerned mostly about current consumption, he likes nuclear power the most. He thinks that's the safest, and he puts gas down at the bottom because he's worried about gas explosions. But if he's looking ahead to the future, now he puts nuclear power down at the bottom because he's worried about how to get rid of nuclear waste. That's going to be a serious long-term problem. So I've described Alice and Bob's preferences in these 2 states of the world, and if you look at this chart up here, you'll see that I've summarized their preferences in the 2 states. So for example, in state 1, Alice likes gas the most, then oil, then coal, then nuclear power, and similarly for Bob, and similarly in state 2. So I said that the Energy Authority wants to take Alice and Bob's preferences into account. Now, Alice and Bob have different preferences, and so what the Energy Authority will want to do is to make some compromise between Alice's preferences and Bob's preferences. So what is a good what is a good compromise in state one? Well, notice that in state one, gas is not a good compromise because although Alice likes gas a lot, Bob hates gas. He puts it down at the bottom. And similarly, nuclear power is not a good compromise because Alice hates nuclear power. And coal is not a good compromise because both Alice and Bob prefer oil to coal. So that suggests that in state one, oil is a good compromise. So the Energy Authority, if the Energy Authority knew that state one is the true state, it would want to choose oil. Now, what about in state two? In state two, gas makes a good compromise. Nuclear power is not a good compromise because Bob doesn't like nuclear power. Alice doesn't like oil, and both Alice and Bob prefer gas to coal. So gas is a good compromise in state two. The problem, of course, is that the authority doesn't know whether state one is the actual state or state two is the actual state. So it doesn't know whether to choose oil or gas. So what can it do? Well, the simplest mechanism would be for the authority to ask Alice and Bob, what is the state? In other words, for the authority to do a survey. But this survey is not likely to be very useful because notice that Alice is going to want to say that state two is the state, even if state one is the actual state. Because Alice in both states prefers gas to oil. Note, Alice prefers gas to oil in state one. Alice prefers gas to oil in state two. So Alice wants to make the authority think that state two is the actual state because Alice knows that the authority will choose gas in state two. So Alice will always say state two is the state. And Bob will do just the opposite. Bob always prefers oil to gas. He prefers oil to gas in state one, prefers oil to gas in state two. He wants to make the authority think that state one is the state so that the authority will choose oil. So Alice will say state two, Bob will say state one, and the poor authority will have no idea what the actual state is. So a survey is not going to work. So what can the authority do? Well, I claim that the solution to this problem is this table here. If you've learned a little bit about game theory, you may recognize this table as a game played between Alice and Bob. It's a game where Alice chooses rows. She can choose the top row, or she can choose the bottom row. And Bob chooses columns. Bob can choose the left column, or he can choose the right column. And then the outcome of the game is the intersection of their choices. So if Alice chooses the bottom row and Bob chooses the right column, notice that gas is the intersection of those choices, so gas will be the outcome. So I claim that this little game is the mechanism that solves the problem. So let's see why that's so. Remember, Alice and Bob know what the state is. The authority doesn't know what the state is. Let's imagine that state one is the true state. In other words, that Alice and Bob's preferences are given over here. Well, what will Alice and Bob do? Well, if Alice predicts that Bob is going to choose the left column, Alice is going to want to choose the top row. Because if she chooses the top row, she gets oil. If she chooses the bottom row, she gets nuclear power. And notice that in state 1, Alice prefers oil to nuclear power. So Alice will play the top row if she thinks that Bob is going to choose the left column. And furthermore, Bob will want to choose the left column because no matter what Alice does, he's better off with the left column. If Alice chooses the top row and Bob goes left, he gets oil. If he goes right, he gets coal. But notice that Bob prefers oil to coal in state 1. So he's going to want to go left if he thinks Alice is going to choose the top row. But he's also going to want to go left if he thinks Alice is going to choose the bottom row, because then he gets nuclear power if he chooses the left column. If he chooses the right column, he gets gas. And Bob prefers nuclear power to gas in state 1. So, in fact, Bob will want to choose the left column. And so we see that a very good prediction of what will happen if this game is played, and state 1 represents Alice and Bob's preferences, is that Alice will play the top row, Bob will choose the left column, and the outcome will be oil. And notice that oil is the right choice in state 1. So in state 1, we have implemented the right outcome. Now, this is what's called a Nash equilibrium, where Alice chooses the top row, Bob chooses the left column, and each choice is optimal for the player given what the other one is doing. It's called a Nash equilibrium after John Nash. Some of you may have seen a movie about John Nash called A Beautiful Mind. If you've seen that movie and you heard how Nash equilibrium was described in the movie, forget everything you've heard, because the movie did a terrible job. This is what Nash equilibrium is, not what it said in the movie, but I'm glad that the movie exists anyway, because it introduced John Nash to the general public. So Nash equilibrium is a very good prediction of what will happen in this game, and we get oil, which is the right outcome. Now, I'm not going to go through the analysis of state 2 because it's actually the mirror image of state 1. For exactly the same reasons that Alice chooses top row, Bob chooses left column in state 1, in state 2, Alice will choose the bottom row, Bob will choose the right column, and the outcome will be gas, which is exactly the outcome we want in state 2. So this mechanism does do exactly what the energy authority wants. It gets the right outcomes in each state. And if any of you are interested in seeing the detailed analysis, just let me know and I can send you these slides, or let the Olympiad organizers know, because they have the slides. So the grand conclusion is that we've solved problem 3, example 3 as well. So I've now shown you 3 examples, and in each case, there was a simple solution to the mechanism designer's problem. But there's a sense in which you might be dissatisfied with with these examples because, in a sense, I did a magic trick for you. I said, here's a problem, and voila, here's the answer. But I didn't tell you how I found the answer. I just showed you the answer. And you might say, well, is there a way of determining whether or not a goal has a solution? In the three examples I showed you, there was a solution, but I could also show you some examples where there's no mechanism that will work. But how do we know that there's no mechanism that will work? If there is a mechanism that will work, how can we find it? Is there a recipe we can follow, an algorithm we can follow, which will generate a mechanism to solve the problem? Those are the sorts of questions that mechanism design is interested in, and that's the reason I got interested in mechanism design myself. If it turns out that the answer to both these questions is yes, that there is a general way of determining whether a goal is implementable. There is a general way of finding an implementing mechanism. Don't worry, I'm not going to go into the details today of why the answer is yes, but if you're interested in some extra reading, you might want to read a paper that I wrote actually quite a long time ago now, over 40 years ago, which explains why the answers are yes. So I'm not going to do that today, but what I am going to do is to try to convince you that there's a lot left to do in mechanism design. One of the nice features of mechanism design is that there are new problems coming along all the time which can be solved using mechanism design. That's what keeps the field fresh. Mechanism design was created over half a century ago, but it's still very active because there are these important problems around that need to be solved. One of them is climate change. We're all aware that temperatures are getting warmer around the world. We're all aware of why this is happening. It's because we're emitting greenhouse gases like carbon dioxide, which are trapping heat. How do we solve this problem? Well, the way to solve it is for the countries of the world to dramatically reduce their greenhouse gas emissions, their carbon dioxide emissions. But there's a problem in achieving this goal because although each country would be very happy if other countries made reductions, no country wants to do this on its own. It's expensive to make carbon reductions because you have to shut down outmoded factories, you have to find new energy technologies, you have to penalize polluters. All of this is costly for the economy. And so no country wants to do this by itself. Now, how do you get countries to make such reductions? Well, you design an international treaty, which countries are willing to sign because they know that other countries will sign this treaty too. And the treaty has to be written in such a way that it not only encourages countries to sign, but it also succeeds in achieving the carbon reduction targets. Now, we don't have such a treaty yet, but I'm confident that we will. Maybe some of you here will be involved in writing that treaty. Writing that treaty is an exercise in mechanism design. That's what a treaty is. It is a mechanism for achieving a goal. In this case, the goal is carbon emission reduction. When the problem is solved, and it will be solved, mechanism design will be the key to that solution. Let me mention another problem. Probably many of you are too young to remember that 10 years ago, there was a terrible financial crisis, the worst since the 1930s. And this financial crisis led to a very severe recession, which we still are suffering the consequences of. Many of the political problems we see in the world today are the consequences of this terrible crisis that we suffered 10 years ago. It's important that we find a way of preventing such a crisis from happening again. Why did it happen? It happens because of a failure of regulation. Just as no country wants to make carbon reductions unless other countries are making carbon reductions, it's the same thing in the financial world. No bank wants to stop making risky loans unless other banks stop making risky loans. How are we going to achieve a situation in which all banks are behaving safely? Well, that's a situation that can be achieved by a regulatory system. But regulatory systems are a little bit tricky because you want to have enough regulation to prevent the financial system from exploding the way that it did 10 years ago, but you don't want to have so much regulation that you prevent innovation and growth from taking place. So you need to find a balance between the two, and finding a balance between the two is a problem in mechanism design. Again, we don't have the final answer on how to design such a regulatory system, but again, all of you here have the opportunity of contributing to that solution. And one final area for the future, this is actually something that I'm interested in my own research. I think it's fair to say that politically speaking, there's great room for improvement in the world today. Many countries have leaders which in many ways are not up to the task of dealing with the most important world issues. And I think these political failures can be traced to a significant extent to failures of the election process itself, failures in the way that presidents and other leaders are elected. And so, as I said, one of my own interests is figuring out better ways of electing presidents. Again, I think there are good reasons for being optimistic about the political future, but in order for these optimistic beliefs to achieve reality, mechanism design is going to have to play an important part. So that's really all I have to say to you today. I hope that you have some idea of what mechanism is all about. I hope you agree that it's an important subject to study. It deals with some of the big issues of the day, and I hope that some of you might even be inspired to try it yourself. Thanks very much. And I believe there may be time for some questions and answers. Can someone run the Q&A session? I don't want to do it.
Hello. Hi, Professor. Here.
Yeah, can one of you, Andre, can you be the moderator for the Q&A? Okay.
Hi, Professor. My name is Hamidi from Malaysia. I have two questions. One is actually...
Why don't you ask one question?
Okay, one question. So I understand that this, from the statistical point of view, we are looking for the local optima kind of things. Will this work for both local optima and global optima? Means that the optimizations of the benefits at what level, right?
So you're asking whether mechanism design can achieve
for both local optima and also global optima.
Well, the purpose of mechanism design is to implement your goals, whatever they are. So mechanism design doesn't tell you what the goals should be. That's up to you to decide. But once you have those goals, then mechanism design tells you how to achieve them. So if your goals happen to be global optima, then you will achieve a global optimum. If your goals are only local optima, then you will achieve local optima. So it's up to you what kinds of optima mechanism design achieves.
Hi, Eric. How are you? Thanks for that. I really enjoyed your talk. I just have a question with reference to the Nash Equilibrium you described on 118. Considering that it's based around, it's within game theory and within the prisoner's dilemma, where the two opposing parties can't communicate, the basis of this is that is it not that we're assuming that Alice knows Bob's preferences and Bob knows Alice's preferences, and in reality, does that actually transpire?
Yes, so you're right. In the little example that I showed you, the energy example, Bob knows Alice's preferences and Alice knows Bob's preferences. That this is back.
It's 118 it was.
Here we are. So yes, the two. Sorry?
I think it's the cake. It's the cake example, right?
What's the,
I thought it was the energy example.
Yeah, it's the energy one, yeah.
So this is the energy example.
Fine.
So in that example, because I'm assuming that they're just the two states, Alice knows Bob's preferences, Bob knows Alice's preferences, but that actually is only for the purpose of this example. I wanted to limit the example to 2 states.
Yeah.
But I could have done this example for the case of 4 states where there are two possibilities for
Yeah.
Alice and 2 possibilities for Bob, and Alice knows her own preferences but not Bob's, and vice versa.
I suppose it was...
That could be
oh,
done
sorry.
too. It's just a little bit more complicated.
Yeah, it was just, and I will put away the mic now, but it was just, you know, when they were taking a distinctive action based on what they thought the other person was going to do, does that not go against the principle of rationality that someone is going to state what is in their best interest? Is that not what you were saying, that they will say that their preference for a fuel source, they will say that preempting what the other person requires or is going to ask for? Wouldn't a rational individual state what they want? No?
I'm
Or
not
did
quite
I
sure what you're
misunderstand
asking.
you? Sorry.
Alice is going to do what's best for her,
Yeah.
given what she anticipates Bob is going to do. That's rational, right?
Okay.
And Bob
Oh.
is going to do what's best for Bob, given what he anticipates Alice is going to be.
Even if that goes against what is in her best interest?
No,
Or are we going to arrive at the outcome
No,
to
but-
come down
but-
the chain, is it?
Bob knows.
Oh, it's back to
Bob
because he
knows
knows
Alice's
what she wants.
Yeah.
Absolutely. Perfect.
So both players are behaving rationally in this example.
Because they have a full information set. Great. Thank
Right.
you.
But even if there were not full information, we could extend the analysis to that case as well.
Good afternoon, Mr. Moscone. Thank you for your lecture. And I'd like to ask you about the interest rate. Can you give the answer, please, on my question? It sounds the following. Will the measure of reducing the interest rate in Russia till the level roughly equal in Europe be successful? And what do you think? Will it be helpful for small and medium-sized businesses, or would it lead to the inflation? Thank you.
So that you're asking the wrong person that question. I am not a specialist on macroeconomic policy. You should ask a central banker that question, not me. Sorry.
Hi, Mr. Maskin. Thank you for your lecture. I was wondering whether you could give any advice for high school students trying to get involved in mechanism design. Is there any way which we can get involved in the field and start to approach these more difficult problems like climate change and presidential elections?
So you want to know how to get into the field? Well, I already suggested one paper that you could read, my old 1977 paper. That's a little bit technical. If you want a non-technical introduction to the field, or you might want to go to my Nobel lecture. If you type in my name and Nobel lecture into Google, you will find the lecture. You'll also find the lectures that Roger Meyerson and Leo Hurwicz, who also got the prize for mechanism design, you'll find their lectures too. That's a good starting place for mechanism design, and all 3 lectures have references to older papers and books, which you can also take a look at.
There's also a book by Roth, I guess. Do you know the book by Alvin Roth?
That's right. That's a popular book that came out a couple of years ago.
Again, thank you very much for your lecture. I just wanted to ask you in this, in this particular example, the energy example, you mentioned early on that the institution who basically decides which type of energy to use doesn't know whether the society and, I mean, whether Alice or Bob are in state 1 or state 2.
Right.
And we have indeed identified the right solutions if the society is in state 1 or is in state 2. But how can we know what to implement if the deciding authority still doesn't know which state the society is in?
I'm sorry, I didn't catch the last part. What is the question?
Yeah, so essentially, how does the deciding authority implement the choice if it doesn't know that the society is in state 1 or state 2?
Well, that's what this mechanism does here. The authority doesn't have to know the states. Basically, Alice and Bob, who do know the states, will take actions which will lead to the right outcome. So in state 1, Alice and Bob will make choices which lead to oil, which is the right choice in state 1. In state 2, Alice and Bob will take choices which lead to gas, which is the right outcome in state 2. So the authority never even has to learn what the state is. It can adopt the right energy choice through observing what Alice and Bob do. And that's the trick that mechanism design uses more generally, to let the participants themselves, through their actions, generate the right outcome.
I wish we could have the entire afternoon for Q&A, but in the interest of time, let's do this. So we collect like 3 final questions,
Okay.
and then have Professor Maskin answer any of his choice. So 1, 2, 3. It's my discretion anyway. Go ahead.
Stanisław Owsiak, Poland. I have a question because during your presentation, I think that I thought that this design theory is very close to public choice theory, developed in the 60s and 70 years, last century. And the question is, what is your opinion? Which theory was first developed in this area of decision making? One question. And second question is related to this point, because I'm a specialist on finance, that we should find the balance, this very elegant statement by you, the balance between regulation and deregulation. And it's very difficult to find this optimal point. And the question is, if, in your opinion, American authorities, US authority, financial authority, did enough to protect society, economy, with comparison to European Union authorities? That was 2 questions. Thank you.
Good afternoon, sir. Your lecture was really interesting. So my question is, in the second example which you gave regarding the sale of spectrum, so we had to give a bid, company had to send a bid, and then you said that the second bid will be selected and then we'll reach the efficient outcome. The one who is willing to pay the most will get it. Wouldn't a normal auction in which everyone will give their bids, that too wouldn't that too be giving us the efficient outcome? The one who is willing to pay the most will get the spectrum?
I'd like to thank you for your presentation. And my question is, in the 3 examples that you cited, there is an unincentivized incentivizer. So for example, in the energy situation, there's an energy company that is not subject to any incentives. However, you said that this mechanism design theory is applicable to situations like presidential elections, in which the people who are deciding the mechanism are by themselves incentivized in the system. So I'd like to know if there is any research already done on this, and if you could give me any indications of like reading material or something, a scientific paper that talks about this. Thanks.
Let me make sure I understand. So you want to know what are the incentives for the mechanism designer himself?
If this theory is applicable to situations where the mechanism designer is himself, for example, in an election system, which is first past the post,
right,
the decision makers are incentivized to not change the decision system. So how can we deal with this kind of situation?
Yeah. Okay, so let me actually start with that. How do we get mechanism designers, governments, to make the right choices? That is a mechanism design question, and that question is answered when we think of the way that government is designed in the first place. When we write a constitution for a country, we are deciding who gets to decide what. And are there, for example, going to be constraints placed on the legislature by the courts? And is the president subject to impeachment by the legislature? All of those questions are aimed at getting government to act for the welfare of the public that they serve. And the answer to your question is yes, there is a literature on constitutional design, and it takes very much a mechanism design perspective. To briefly answer a couple of other questions, so I described, when I was talking about the spectrum auctions, the Vickrey mechanism, which has the highest bidder win at the second highest price. One way of achieving this mechanism is to have what is called an open auction, in which companies call out bids openly under the restriction that each successive bid must be higher than the previous one. And then the auction stops when no one wants to make a higher bid. If you think about that auction for a minute or so, you can see that it's actually the same as the Vickrey auction, because that auction will end precisely when the bid reaches the value of the second highest bidder. So the two are equivalent, and that's actually something that Vickrey himself showed. Over here, there was an example, there was a question about which country got financial regulation the best? Was it the US? Was it the European Union? Actually, I think the right answer to that question is Canada. It's interesting that Canada, which is right next to the United States, suffered no bankruptcies, no bank failures at all during the financial crisis of 10 years ago. And that was not because of luck, it was because Canada had serious and effective financial regulation, much more effective financial regulation than the United States did. So while in the United States there were hundreds of bank failures, there wasn't a single one in Canada. I think that teaches us something.
So with that, please join me in thanking Professor Maskin for his inspiring lecture. As a small piece of housekeeping, there seems to be lunch available right now, and the volunteers are there waiting for you to meet you there and to take you to the place.